So in lecture, we left off talking about how an action potential is generated, how we have those moving of sodium ions, opening gated channels, causing more sodium to rush in, causing this depolarization stage where we've got that huge change in membrane potential going from -70 all the way up to +30. When we talked about repolarization, having those positive potassium ions leaving out of the cell to get it back to normal, although sometimes too many leave and we go into hyperpolarization or below our resting membrane potential. And then eventually using our sodium potassium pump, we get everything back to normal, back to our resting state. Mike, this last little bit kind of talks about some different things that can happen or sometimes not happen to actually have all of these steps to generate the action potential. The first one is that not all depolarization events actually produce the action potentials. Mostly it's because they haven't met threshold. They haven't hit, even though you can become depolarized, and this can go from -70 to -60, if it doesn't get to that -50, -55 threshold mark, it's not going to generate an action potential. So for an axon to fire, for it to actually cause a full action potential, open up all of those gated channels, they have to reach threshold. Now, Mike, once it's depolarized by around 15 to 20 millivolts, once it goes from that -70 to around -55, 50, that's when lots and lots of sodium rush in, more sodium rush in than potassium are leaving, and you've got a positive feedback because once some sodium go in, more sodium go in. But it's not every depolarization event because it's, a few sodium can go in and it become depolarized, but if it doesn't hit that threshold, action potential is not going to happen. Now, whether it happens or not, we call it an all or none. Either you're going to generate an action potential and it's going to happen completely, or it's not going to happen at all. It's once you hit that threshold, all the channels are going to open, you're going to generate the action potential. If you don't hit the threshold, nothing's going to happen. Now, Mike, it's, one or the other. You're either going to fully generate an action potential or you're not at all. Now, once we've generated the action potential, we're going to say we hit threshold, we've generated the action potential. That electrical impulse that we just generated has to move. That's the propagation. So we have to have that electrical impulse moving as a signaling device. We have to get that electrical current to wherever it needs to go. Now, how it ends up happening, as one electrical impulse starts, we opened all those sodium channels, we created that huge depolarization event. It can cause the sodium to go in other areas as well. So it causes local currents to depolarize in adjacent membranes. And so they're kind of telling all their friends in the neighboring clubs, and I'm like, how to get in. And so I'm like, it caused more local currents, more action potentials away from the original one. I'm like, if we're gonna have this analogy to, a downtown region, one bar, those sodiums go in and they figured out how to get past the bouncer. Well, then they tell the next bar about it, and the people at that bar tell the next bar, and they kind of keep going down from one bar to the next. And I'm like, generating action potentials along the way. Now, that original action potential, until everything gets reset, I'm like, all the sodium channels are inactivated. So once that first bar, that first club causes an action potential, nothing else happens right there. It's just kind of a little series of events causing neighboring channels, which is how that electrical current moves along. And it keeps moving. It's self-propagated in non-myelinated action or axons. Each successive segment, each one depolarizes, then repolarizes, and then tells the next thing. Propagation of moving this along in myelinated axon does differ a little bit, and we'll get to that. So I'm like, it is this kind of subsequent slow telling one bar to the next bar to the next bar to the next bar how to do this. Myelinated actions, they're a little faster, and I'll show a little picture on how that can happen. Now, this is just showing if this is your original club, your club axon, if this is the original club that figured out how to have this depolarization event happen. Some of these sodiums got in, my depolarization happens, Well, and it tells the neighboring one, it tells the neighboring one, it tells the neighbor one, Mike, and at some point we will record, um, you know, when the electricity gets to certain areas. And Mike, with that membrane potential, we can look to see this happening. Now, once an action potential has been generated, once you've opened all of those sodium channels, you've had that huge depolarization event, and all those sodium channels are still opened. I'm like, during that time period when all of them are still open, we've entered in what's known as an absolute refractory period. It means that only the action potential that just was created is the only action potential that can be generated. We can't create another action potential on the same place that we just generated an action potential. You can't have people sneaking into a bar, and I'm like, and you can't have the same people sneaking into bar that are already sneaking into the bar. You've already had some go in. You can't have those same ones go in. They're already there. This ensures that all action potentials are all in one event. Once we have it happen, it's going to happen, and it's going to happen fully. And it ensures that we have a one-way transmission, that we're going to have a starting place where we generated this action potential, and it's going to propagate down the line in a one-way transmission. We're not going to go a little bit down and then come backwards to where that original action potential was generated. So absolute refractory period, absolutely, you can't open more sodium channels. They're already all open, and you can't generate another action potential while they're still open. Now, my analogy for an absolute refractory period is when you flush a toilet. I'm like, after you flushed a toilet, you can't flush it again right away. Everything has to reset itself. So when you're in that absolute refractory period, you can't do it again. You can't reflush the toilet until it resets itself. Now, right after that absolute refractory period, those sodium channels are starting to go back to their resting state. They're starting to close. The doors are closing. The bouncers are going back. And I'm like, they're starting to return to their resting state. Some of the sodium channels are still open, and you have repolarization starting to occur here. Now, it hasn't fully occurred. We haven't gone back to our normal state yet. I'm like, but we're slowly getting back to our normal state. Now, this means the threshold to create an action potential is elevated because the inside of the membrane is more negative than it was at the resting state. When we're in that hyperpolarization state, too many potassium ions, positive ions, have left. We've moved some of our, and we've moved some of our sodium out that were more negative than the resting state. Our resting state was negative 70. Hyperpolarization can easily be negative 90. Means for you to get back to threshold, it's going to require more. Negative 70 to negative 55, that change around 15. Negative 90 to negative 55, you're going to need a stronger impulse, a stronger depolarization to change that about negative, 35 difference. Example, absolute refractory period, all your sodium channels are open, you haven't reset yourself. Only one action potential can be generated. In the relative refractory period, you can get into that hyperpolarization, negative 90, maybe even more. So for you to reach threshold, negative 55, way up here, it's going to require a stronger impulse. It's not impossible, but I'm like, at this point, the channels have been resetting themselves or getting back to normal. It's just during this stage, it takes a little more. Again, back to my flushing toilet. During an absolute refractory period, can't flush a toilet at all. Relative refractory period, when it's, the toilet is slowly starting to reset itself and you might have to flush again. Now to do it, it might not be the best flush, and you might need a stronger pushing it down to make it happen, but it's possible during that relative refractory period. Now I said, as we're moving these electrical currents, these action potentials along the neurons, and whether a neuron is myelinated or not can make a difference on how fast that information, that action potential, can travel. Myelin helps insulate, and it prevents the leakage of charge, which means ions can't sneak out, and so whatever ion change we created, it stays there. Now, that means when action potentials, and we have moving of ions, but these are insulated ions, and things can't get in and out around those neurons. So where are we going to correct, where are we going to create those action potentials if we can't have moving ions in and out? Well, it only happens at the gaps between the neurons. It's called something known as saltatory conduction. It only happens in myelinated axons, and those action potentials, where the sodiums are, they're located at the myelin sheath gaps where we don't have lots of myelin. I'm saying that right. So action potentials are only generated at the gaps where there's no myelin, and electrical currents of those action potentials will jump from gap to gap. Now, the word saltatory conduction, comes from the word saltare, which means to jump. Our action potentials are jumping. Down here is showing how that's happened. Here are your myelinated axons. Now, it's only in these gaps between the myelin where you're going to find those sodium channels that can open and potassium channels that can open to create those action potentials, which means for any type of action potential to self-propagate, it has to create an action potential here and then jump over here and then jump over here. Non-myelinated axons, and it kind of does a slow, steady jump, one step to the next. And I'm like, in bare plasma membranes, because you're going to have leaking ions, the action potentials die pretty quickly. And I'm like, usually how I try to compare this, I like analogies. A non-myelinated action is when you're walking down the stairs. And I'm like, going one step at a time. It's a nice, slow, steady, eventually gets you there one step at a time. In a non-myelinated action, well, they have to jump. And so if you're going down the stairs, 3 steps at a time, you're jumping steps, you can go down the steps a whole lot faster. If you can skip steps and go one step, every, third or every fourth steps by jumping the steps, you can go a lot faster. And that's what's happening in these action potentials when you have myelinated axons. They can jump from, over several steps, and so we can send electrical impulses a whole lot faster. Now, although we do have action potentials that are moving from along axons, at some point, one neuron has to send this information along to another neuron. So we have to go from neuron to neuron. Well, neurons are connected to each other by synapses, just the junctions that allow action potentials to go from one neuron to another neuron. This is just showing some examples, and I'm like, that you can have action potentials traveling along these axons, but this neuron's also connected to this neuron, and this one's connected to this one, and this one has a connection to this one. And so we can have action potentials traveling along. Here's an actual picture of axons attached to other neurons. So they can easily, go from one neuron to another, so that the information, that electrical information, gets sent to wherever it needs to go. Now, some review at the end. As a general rule, the greater the potential difference in charge between 2 points, the higher the voltage, which means if you start at -70 and go to +30, that's a difference of 100. And I'm like, you're going to have a higher voltage. You have more moving ions with the greater the difference between those 2 points. Sodium ion concentration in the cytoplasm of a neuron increases when the voltage gate and sodium channels open, meaning they're going to go in to the cell, into the cytoplasm. The type of potential that does not decay with distance are action potentials. The other ones slowly go away. Maintenance of the resting membrane potential, the top things that do it, and I'm like, are your pink and your orange. And I'm like, it's that sodium-potassium pump that is moving sodium where it needs to go and moving potassium where it needs to go, and it requires ATP to do that. Depolarization of the neuron is always referring to a reduction in membrane potential. And that's because we start at -70 and we go to not as negative. We're not as negative. You're reduced in negativity, if that makes sense. And I'm like, so you have a reduction in membrane potential. Neurons generally repolarize once the membrane potential reaches approximately +30 millivolts, because when you get up to that point, all the potassium channels are going to open and it will repolarize or reset itself. The point in which the all or nothing principle or action potential generation is reached is once you hit that threshold, that around plus 50 or negative 50, negative 55. During the relative refractory period, both orange and yellow apply. The threshold is substantially elevated, which means you're going to need a bigger stimulus for you to get to that negative 55. So only an exceptionally strong stimuli could actually trigger your action potential. And the last question, the location at which a neuron interacts with its target cell or another neuron or a muscle cell or some effector cell, where that neuron interacts with something else is called the synapse. That's that junction in between.